About 25 to 30% of the CO2 that's released from fossil fuel combustion ends up in the ocean. That lowers pH, and it also changes something we call saturation state, which is the corrosivity of that water.
Based on the chemistry of the water and how marine life respond to chemistry, the kinds of organisms that we think are the most vulnerable are the ones that build a shell. So oyster shells, clam shells, and corals.
I think the things that are most important to the public to understand is that what this issue is threatening is some of our food supply. There are people's livelihoods and generations of watermen who rely on producing oysters and other shellfish. So when we talk about ocean acidification, what we're talking about is a change in carbonate chemistry of the ocean due to the increase in atmospheric CO2 from fossil fuel combustion, as well as other local processes that change that chemistry. And so the issue comes in is that we're changing that chemistry faster than we have in the last million years in the Earth's history. And that's having predictable consequences on the chemistry as well as consequences on the organisms that we're just starting to understand now.
So we've identified the Oregon coast as one of these early impact systems. So our chemistry is already changing and has changed dramatically.
The waters that reach Oregon's coast, if you stand on the coast and look out and see this great blue expanse, you think, oh, that's just one big bathtub of water. You're not quite sure what's there, where it's coming from. But over the years, we understand very well how that water gets there. And that water reaches Oregon's shore from far across the North Pacific, off to the northeast of Japan, actually. When it's at the atmosphere, it gets the oxygen and the CO2 from the atmosphere mixed into it. It's cold enough there that the water gets dense or heavy and it sinks down to beneath the waves to about a couple hundred meters and starts this long journey across the North Pacific. And there are actually two branches. One of them comes across the northern Gulf of Alaska. Another one takes this amazingly convoluted route. Along that path, the oxygen gets lower, the CO2 goes up, the pH goes down, it gets more acidic before it reaches Oregon shores. So if you think about the rising CO2 levels in the atmosphere, the water we're seeing at depth off Oregon has the signature of many decades ago.
Even if we absolutely stop the CO2 emissions today and cap the atmospheric levels, there's still a 30 to 50 year increase we're going to see before that carbon, at least along our coast, works its way out.